So, hi everyone. My name is Enrico Bottazzi and I do MPC FHE research at PSE. So let me explain what this means. First of all, MPC stands for multi-party computation. FHE stands for fully homomorphic encryption, which is a technique part of this MPC, which is an umbrella term. And PSE stands for Privacy and Scaling Exploration, which is a team inside the Ethereum Foundation. So the title of the presentation is On Chat Control and Privacy Preserving Application Beyond ZK. Chat control is the name that has been given to this new regulation that is in the process of being approved by the European Union, and we are going to get to that later. And the main thesis of my presentation, what I want to convince you of, is that there's many techniques that can be used, many cryptographic techniques that can be used beyond ZK when you want to build a privacy-preserving application. So we're gonna start with this quote that is like, when all you have is an hammer, everything looks like a nail. So it's most of the time is using like a business context, and basically means that when you only have one tool at your disposal, when you have like expertise in one tool, you try to use it everywhere. So everything seems to be a nail to you, and basically you apply this solution to every problem without considering any other tools that might be at your own disposal. And I'm going to modify this quote that when all you have is ZK snark, everything looks like a single player application. So just remember this, and we're going to get to that later. So this is from a presentation that Brian from 0xSpark made at ProCrypto in Istanbul. And we don't have to go through that, but it's just to explain you. This is like a very good overview of all the cryptographic techniques that are at our own disposal. And as you see, like the ZK snarks, or like ZK proof, are just a small quadrant in this graph, but there's like a lot more tooling available at our disposal, and we're gonna get through that in the presentation. So what is chat control? So chat control is something that I guess not many people speak about, or at least like on the news, you never heard about that. But it's this regulation that is in the process of being approved by the EU, and basically it mandates messaging apps to perform scanning on the content being exchanged through these messaging apps. So for example, like now when you use WhatsApp, Telegram, Signal, you see this end-to-end encrypted sign, and it actually means that WhatsApp itself or Telegram itself cannot read your own message. Only you and the person you are sending this message to have the key to decrypt and read this message. But this regulation is basically mandates this application to scan the messages, the images, the text, in order to prevent the proliferation of child pornography content. So of course, we all want to avoid like spreading child pornography. But the downside of that is that it basically leads to surveillance of all our communication. And this is not good, of course. So we want to build, like in this application, what we are trying to do is basically start from the problem statement that we described before, like the potential effects of this chat control. And we are going to build a solution that gets basically both sides happy. So the EU and, well, say all the world is happy because there are no child pornography being shared on these messaging apps, but at the same time, we preserve the confidentiality, the privacy on our data, basically avoiding this kind of North Korea-like state surveillance. And we're going to use cryptography and the tooling that we described before to do that. So the first tool that we are going to analyze is actually not cryptography. It's more, let's say, statistical tooling, which is machine learning. So for each tool, we're going to go through like a very quick and not complete introduction, technical discussion. And first of all, like the important thing about machine learning is to separate it across two different phases. The first phase is the training phase. So in this training phase, we basically feed a lot of data into this model that we want to train, that we want it to learn stuff. So in this case, our goal is to train a model that is able to tell whether an image is like child pornography or not. And the specific type of model that do that are called convolutional neural nets. And the training phase will basically be about like feeding this model with a lot of data. Some data will be images of child pornography, some will be other type of images. And every time the model will make a prediction, and we are gonna tell based on like some human will be able to tell, no, the prediction was wrong or the prediction was right. So if we present them with a cat and they say it's child pornography, we're gonna tell it's wrong, and then they will basically modify their models, modify their parameters in order to adjust to that, while every time they make a right prediction, we are gonna kind of reward them. And the output of this training phase is something called weights. So it's just like a vector of floating points that might seem like random, but it's actually the encoding the identity of this model. And companies put a lot of money into the training, and these weights are very precious. Like they kind of encapsulate all the competitive advantage that, for example, a company like OpenAI might have. So we're gonna get to that later as well. And then there's the second phase, which is an inference phase. And this happens when the model is presented with like new data that they have never seen. And based on the training, they're gonna make prediction. So we present them with a new image, and they're gonna say whether this is like child pornography or not. And of course, more the data we fed into the training phase, more accurate the model will be, and more likely it will be to guess correctly. And just also to make another analogy with something that you might be more familiar with, every time you enter a prompt into ChatGPT, this is inference. So this is something that is presenting with data that the model itself has never seen, while the training phase was done like probably months or years ago by OpenAI within their own premises. Okay, so we finally get to a potential solution to the original problem. We see like this diagram, we're gonna see it many times across the presentation. So we have a user and we have the messaging app server. In this setting, the user is gonna sharing the image, in this case, the content that they want to send to someone else, to the messaging app server, which will run this CNN inference starting from the weights. So we know what are the weights and the image. And as a result, if the model say that the content is benign, the user will be authorized to share a message. While if the model says that the content is malign, will be like report the user or just not let them share the message. So we're gonna always analyze a solution according to these two desired goals that we defined at the beginning. So, okay, first of all, yes, it avoids child pornography because, let's say, we assume that the model is accurate enough to judge whether something is child pornography or not. So, one thing is achieved. Well, the big problem is that this thing, so the image is actually being shared by the messaging app server to the messaging app server. So this solution doesn't avoid mass surveillance. So this is bad. We get to a second attempt to find a solution. So this is basically the same as before, but the only difference is that now the CNN inference function is run on the user side. So this is, as you see, like the image never leaves the user, which this is good. This is avoiding this mass surveillance thing. But there's another problem. Like in this design, the assumption is that the inference is run locally by the user. So when we say locally, we mean outside of the messaging app. And outside of the messaging app means that the messaging app doesn't have any control of this computation being run. So potentially an attacker here. So an attacker is someone who's actually trying to share a child pornography image without being detected by the messaging app, can simply just share with the messaging app server the output, and of course if they are not an attacker, they will share like benign, and this output can come from anywhere. Like the messaging app doesn't have any mean to know that this output is the result of this computation. Or also another attack that can be performed in this scenario is that the user can replace the image that is trying to send with an image that is benign. So they run the model, it will result benign, share, but then when it comes to sending the image, because the messaging app has no control, they will actually send the image of child pornography that they want to send. So we claim that this solution doesn't avoid child pornography. We're gonna now go with like the second tooling at our own disposal, which is the ZK snarks. And again, we're gonna explain very briefly how ZK snark work. So the first thing is to define what is a computation. So it's very trivial, but it's worth defining it. There are like inputs on the left. There's some program inside this box at the middle, which in this case is the program is like the CNN inference, and on the right we have an output. The problem of the previous solution was that there was no way for the user to prove to the messaging app server that they were actually running this computation and not something else. And it seems something that it has no solution. Like intuitively, the only solution to prove to someone that you run a computation on some input in order to get some output is to let them redo the same computation again. But, actually there's a solution to that, which are ZK snarks. So, like the difference is that you kind of perform the same computation inside this so-called circuit, ZK circuit, and what you get is compared to the previous solution, is a proof pi, and starting from this proof pi, the verifier, which in our example is the messaging app, will be able to tell that this computation was run correctly according to the rules that are defined in this box. And there's also another good thing about this ZK snark. So the ZK stands for zero knowledge, and it allows the prover also to hide some of the inputs of this computation. So they can also hide the image itself, which is desired in our problem. So we get to a third solution for our problem, for the chat control problem, and the difference is very subtle. But you see that now they are not actually running the CNN inference, but they are running this ZK CNN inference, and as a result of that, the output will be also attached with a proof pi, and the messaging app server will be able to verify this proof pi. So once this verification is performed, then the messaging app server is confident that the user run actually this CNN inference function on their local device, and they're not just giving them some output out of nowhere without running any function. And again, according to the output, and if the proof is verified, they can either authorize or report the user. So again, this solution is able to avoid mass surveillance because the image itself never leaves the user device. So the confidentiality of user data is safe. But there's a problem that I didn't mention before, but it's pretty severe. In this case, the user have control of the weights, so they touch the weights. And there's a security attack on that, and there's also some, let's say, business risk to that. The security attack is that once the weights of a machine learning model are public, there's a risk of something that is called adversary attack. So the user basically can now try to use this model many times and try to learn its behavior, try to learn how they make this prediction, and they can also try to understand how to trick this model. So I don't know, they might realize that every time you put I don't know, a yellow t-shirt in the model will not be able to detect child pornography. So it's not good that the user has access to the weights, because they can perform this type of attacks. So we claim that this solution doesn't avoid child pornography, because this type of attack can be performed by some pedophile, and they can still be able to access to share the images. And the last thing, as we said before, is that the weights are something really, really precious for like a company, for someone that has trained this model. So this solution will probably also not make a lot of business sense, because I don't know, let's consider that the messaging app has been trained a model, and they are now using this model as a competitive advantage, claiming we are like the most secure messaging app because of our model. As soon as these weights are released to the public, this competitive advantage is basically nullified. So we haven't found a solution yet. But like we actually realized something while trying to brute force solution. We realized that ZK snarks are a single player privacy preserving technology. So this is, I'm gonna explain it to you now. Like ZK snarks work when there's like a party that has like a set of data, and they want to perform some computation on top of this data, and they also want probably to hide a part of this data. But we noticed that in the previous application, we have a sort of conflict. Like the image is private to the user, while in an ideal world, the weights are private to the messaging app server. But there's really no way to design such, let's say, multiplayer privacy preserving technology using ZK. And you can think, but I think there's no way. And that's going back to the title of my presentation, that ZK Snark is not like this solution fits all privacy preserving apps, but there's like some more technology that we can use in our toolbox. And this gets us to secure multi-party computation, which MPC was what you saw in the title, like in my job description. Okay, so before getting into like the, let's say, slightly more technical explanation of MPC, let's make a mental experiment, which is, by the way, not something that I just came up with, but even when you read papers, like the security model of MPC is defined using this mental experiment. It's called like simulation real paradigm. So imagine that there's like this trusted third party. So this party is very trusted, is uncorruptible, and everything you tell them to do, they actually do. And this trusted third party receives the inputs from the user, so the image from the user, the messaging app server shares with this trusted third party the weights. The trusted third party is trusted in the sense that they maintain privacy over the data. the trusted third party will never reveal the image to the messaging app server and will never reveal the weights to the user. And this trusted third party is also trusted in the sense that they're gonna run this function as they are supposed to. So they won't deviate from the protocol and do something else random. So in this scenario, we kind of achieved everything that we wanted under the assumption of the existence of this trusted third party, because the images are never shared to the messaging app server, while we still have the inference function being performed on this image. And also, it makes sort of business sense because the weights are not shared with the user. So now, basically, we can simply switch from this mental model of existence of a trusted third party and replace this third party with some mathematical and cryptographic primitive, let's say. So, of course, in the real world, there are no trusted third party, and we cannot rely on that for our system. So we replace this with a multi-party computation circuit, and in reality, what that means, like inside this box, like the user and the messaging app server will keep like exchanging messages with each other, and come up with a solution, with an output that basically can be shared with the messaging app server, and of course the user and the messaging app server won't ever be able to know the input provided by the other party. So as we said before, this solution ticks all the boxes. It avoids child pornography, it avoids mass surveillance, and it makes business sense. And the point of that is that we were finally able to find a techniques that allows us to perform computation, so the computation defined in this circuit, on inputs that we want to keep private to the other party. And this is why this is a multiplayer privacy preserving technology. And you can think about like other type of application in the world that are multiplayers. So for example, like voting application are multiplayers, or bids like auctions are multiplayers. And in this type of application, there are still applications being built using ZK, but I think that they are not like the right fit for ZK, and you can come up with better solution using multi-party computation technologies. So there are issues. Of course, it's not like as good as I presented. I kind of list over many complications, and like one complication is the bandwidth cost. Bandwidth means like the amount of data being exchanged. So in this, basically the amount of data being exchanged inside this box, and this is true especially for two types of MPC techniques, which are garbled circuit and linear secret sharing. And this is a problem considering this application, because we assume that the user is running this whole thing on their smartphone probably, so they might not be able to support this amount of data being exchanged, or it will probably cost a lot for a user. And there's like another type of MPC technique that is called fully homomorphic encryption, and in that case there's no big deal of bandwidth cost, but the cost here is on the computation side. So it will probably cost a lot in terms of like CPU to run this whole circuit thing. So we can still say that we said before that this solution has business sense. It has business sense under the assumption that companies are let's say they are okay in spending money in building a technology that costs them more in order to preserve privacy of the user. So I'm not sure that this makes business sense, actually. And another kind of subtle but still very important issue is the one on the inputs. So every time someone enters an input to this circuit, there's somehow a requirement to prove that this input is the actual image that then the user is going to send to his friend on the messaging app. And this is actually what I worked on, but my original idea was to make a presentation about this, but you wouldn't understand anything if I started with that. So I basically started from the very beginning in order to do that. Of course, I won't now explain that, but if you're interested, I have like some content to share with you. And lastly, there's also another issue, which is like this model is able to convince both the parties that this computation was performed according to the rules. But when it comes to proving it to someone else, so for example, let's say that the European Union goes to WhatsApp and asks them a sort of a proof that all the messages being exchanged were actually went through this process. Well, there's no technical way, like a cryptographically secure way to guarantee that. And in order to do that, we'll probably need to wrap all this like MPC circuit inside another ZK snark. And this will create even more overhead and even more cost for the company doing that. So let's get to the conclusion. So the first thing that I tried to convince you during the presentation, and I hope I did, is that ZK is not this one-size-fits-all solution, but this is just one part of the tooling at your own disposal. And most of the time, I guess that the approach shouldn't be, okay, I have a technology in hand, something that is cool, something that is hyped, and try to apply it to a problem. Like, you shouldn't reason like in this backwards way. Most of the times, the best way to approach things is like starting from a problem, similar to what we analyze here, and then go through the tooling, go through like some papers, and then try to understand which are the best that can fit your problem. And also, what you end up most likely discovering is that the solution will be built as a mix of this tooling. So, for example, in this case, let's say we use free tooling, which are ML, which are ZK, and MPC too. And I feel that it's very difficult to abstract when a specific tooling might be useful unless you give a problem. So only in that context it makes sense to define which technology might be more useful. So my presentation is over, and I leave you to this QR code that leads to my blog post, in which I will share an article related to the presentation very soon. Thank you.
Yeah. Hey, I don't know if it's a question or more like a thought. It's like, what do you think? So let's say you have these bad actors that are sending these contents that are objectively bad for everyone. So I can imagine, okay, I go through all this process and I make like this super advanced system, right? But I don't know, someone can be like, I'm gonna just encrypt my stuff with, I don't know, AES, and I'm gonna send that over, and it's gonna be just arbitrary bytes. So we would need a way to be like, okay, this is like the format of content that is allowed, like, I don't know, just your thoughts on that.
Yes. So I kind of let's go back to our diagram. Like there's like also another step here, which is the one in which you actually share the content with, let's say there's another party that is like user B, and then after this is authorized, then you're allowed to share the image with your friend. So in that case, yeah, of course the image will be encrypted, and as you mentioned, there needs some way to prove that the image that is encrypted and is shared here is actually this image. So yeah, I guess that there's also some technique that must be used there to kind of, again, relying on cryptography solely, that the image that was here is the same that is sent over here. And I don't know, I can think of, for example, you can hash, you can, for example, like generate inside this circuit an hash of the image, and then prove that like once you encrypt the image to send to your friend, the hash of the image that you're encrypting is the same hash of this image. Well, I guess you can be creative.
No, because I was okay. Yeah, no. So I was thinking, oh no, I take a picture of my cat, and then somewhere in the image, I just encode bytes in my own. So when I'm saying I'm playing like against the system, and if I want to play against the system, it's like you can get very creative in the ways you can play against it, because you could be like encoding in noise in the image, you can be encoding, oh no, ICBM nuclear codes, whatever, you know, and stuff like that. Yeah, I don't know, that's just a thought that it's going to be like very complicated. I think it aligns with your talk that it's going to be really complicated to get right.
Yeah, of course it's not like a self-containing presentation that I don't claim to have like the solution. It's just like proposal that might be enriched if you want to get it to production, of course.
Yeah, maybe it's a silly question. Would it be possible at all to have a classifier that can distinguish between the two kind of images, but without encrypting it? So while is it encrypted, or would that implicitly decrypt the image?
Yes, good question. So I guess that this, as we said before, there are like different techniques of inside multi-party computation, and one of this technique is called fully homomorphic encryption, and this is exactly what you're describing. So I can encrypt a message or an image, send it to you, you run this model on the image still being encrypted, and what I get back is like the output. So I still have the key, I'm still able to decrypt the output, and then I will share with you the output and saying, yeah, this is benign. So it kind of, like, honestly, it achieves the same thing, but it's more like a different, it's a kind of a slightly different technique and slightly different setting, but it's still inside this category of multi-party computation because it has the same outcome, the same functionality, basically.
Here behind one, I'm interested in some sort of production cycles. So, for example, when you are doing this research and then you propose certain solution, can you explain like how much time it could take to produce something even within the PSC based on whatever Macy and other solutions experience, to understand from inside, is it like 1 year, 5 year? Because sometimes no one talks about real timing, and it's all right to postpone timing. It's normal to do pivot. So yeah, and also it would be nice to also if you would mention how much time you need for research. So generally speaking, a production would be break on research and delivery in that sense.
Right. Yes, great question. And like, of course, if you ask like a researcher or an engineer, probably they will underestimate a lot the time that it takes. So I don't know, for me, like when I see a problem like this, I see that there are like papers and there are techniques that are describing a solution to that. So I would say that it's just a matter of applying or sitting down and coding and building something like that. So probably to build a proof of concept, a very elementary proof of concept of this will take maybe 1 or 2 months, but then like bringing it to production is something completely different that I personally never did, because even at PSC we are like we're not interested in building this stuff to huge scale, to production. I think, well, I'm speaking most about how I feel things are working, is that our goal is mostly like to inspire, to demonstrate that something is possible, and then it's like companies and business will basically take this idea and then build a production ready thing. So I can tell you, I don't have the experience, honestly, to tell you how it will take to bring it to production.
Okay, I have a question regarding the regulation itself. Obviously, from the presentation, we figure out that still we don't have a perfect solution for this. But in terms of the regulation, is the EU open to like computational networks like this, or do they want strictly like would they trade privacy for removing child pornography in this case?
Yes, that's a very good point. So again, I'm not like a lawyer, and I haven't read through like the whole proposal, but from the articles that I saw, yes, they are ready. Like they open for the possibilities of having this being enforced without privacy being destroyed, basically. So like there are also other technologies that I didn't mention. There's one called perceptual hashes. That is something less sophisticated than this, but this is also some solution that is kind of able to mitigate the risk on the confidentiality of user data. So it's not that I also want to say I didn't have the feeling that they are trying to making this proposal pass just to surveil people, which is something that will probably happen in other countries. I guess there's good faith from the EU in that, and they are actually worried about this problem, and they don't necessarily want to surveil ourselves.
Any more questions? Can we have one massive round of applause, please?